Hi, everyone. Thank you for joining my talk and hope you all are doing fine in in what's been a very unpredictable year. To introduce myself, I'm Lakshmi, a software engineer on the streaming platform team at Lyft. And today I'm going to talk about how we enabled zero downtime upgrades of Flink applications on our Kubernetes based infrastructure. Before I dive into the specifics, I'd like to walk you through a brief history of our deployment infrastructure at Lyft for Flink applications. We started deploying Flink at Lyft in late 2017 on bare metal EC2 instances. And this was quickly followed by our other abstraction layers like our streaming SQL platform and Beam Python jobs, all of them deployed on bare metal EC2. And then later in 2018, early 2019, we started working on a Flink Kubernetes operator that we open sourced in mid 2019. That sort of formed the core crux of enabling Flink deployments on Kubernetes at Lyft. And with that infrastructure in place, we were able to move all of our Beam and Flink jobs to our newer deployment stack. And this unlocked our ability to perform more flexible deployments. And today I'm going to talk about one such deployment strategy that's zero downtime upgrades. To begin with zero downtime upgrades, it's good to have context on how a deployment on Kubernetes actually works. As a user of our platform, you might define your job in what we call a job definition or a custom resource definition. And we use a templating tool called JSONet to allow users to write this job definition. And usually it's much easier to write it using some kind of templating tool than have them write hundreds of lines of Kubernetes YAML. This job definition specifies all characteristics that your job might need, like the application name, the jar, the entry point class, Flink configuration, the shape and size of your Flink cluster, etc. The Flink Kubernetes operator is constantly watching all job definitions. And every time there's any update to any job definition, it tries to apply that update to an existing job, if there is one. Or if you're creating a new job, it creates a new Flink application for you. And we use client-side tooling, command line tooling for performing any ad hoc operations on the Flink application, like restarting the cluster, deleting the cluster, getting the status of the cluster, etc. So what actually happens during an upgrade? We start off with a job running, and the user may update the job definition. The operator recognizes that there's an update to the job definition. And what happens next? It first creates a new Flink cluster based on the updated definition, and then cancels the existing job with a save point, and submits a new job to the newly created cluster. And finally, when the new job is in a running state, the operator declares victory and goes back to watching for updates in the job definition. So during the course of this upgrade, we start off with a job running. When the new cluster is created, the old job is still running. When the cancel with save point hits, we no longer have age Flink job running across either of the two clusters, the old and new. And once the submission is successful and the new job starts running, we now have a job running. So as you can see here, we incur a downtime between the cancellation with save point and until the new job is successfully in a running state. And this downtime, it's important to understand for Flink applications, does not mean data loss or is not in the same sense of downtime for stateless microservices. What it actually means is that there is no forward progress being made on your input data sources and your data processing because there's no Flink application running. So this could manifest as consumer lag on your Kafka topic or iterator ages being high on your Kinesis stream. And it's usually the lag is correlated with application characteristics because it totally depends on how long it takes to cancel with save point an application. While some applications are tolerant to this delay in data processing, we have use cases at Lyft which rely on our platform to do real-time machine learning feature aggregation, like our dynamic pricing use case. And for those kinds of use cases, any kind of delay during an upgrade process is detrimental to the quality of the results being produced. So, hence the case for zero downtime deployments was created. One of the primary requirements for zero downtime upgrades, as is obvious from the name, is that there should be no period in time during the course of the deployment when an application is not making forward progress. So, what this means for our state machine that we just saw is that we can no longer have that point in time where there's no Flink job running. In order to satisfy this requirement, we introduce the concept of blue-green deploys. You might have heard this term in the stateless microservice land, where a parallel application is brought up during an upgrade. And once the new application is validated and verified, the router or the proxy starts routing traffic to the new application, and the old one is either toned down or used for other kinds of testing where it's shut off. Similarly, I will walk you through what blue-green deploys means in the context of Flink applications. So let's assume we start off with a old job running like we did before. We'll call this the green job. And the user makes an update, and the operator recognizes the update. And now it starts creating a new cluster, which we'll call the blue cluster. And during this time, the green job is still running. The operator then save points the green job, does not cancel it, submits the new job with the save point to the newly created blue cluster. And now at the end of this upgrade flow, we have not one, but two jobs running. At this point, it might be tempting to stop this entire deployment flow here because you have a green and a blue job running. But there are a couple of things that we might want to do after this point. Firstly, as a user of a Flink application, you don't want two jobs to be running endlessly. At some point, you want to sort of verify your updated job, in this case, the blue job, make sure everything looks fine, and then you don't really have a purpose for the green job anymore. And secondly, when two jobs are running, you have the blue and the green job producing data to sinks, and you might have downstream consumers of those sinks. And you do not want the downstream consumers to start consuming data from the newly updated blue job until you can verify the update and validate that it's doing the right thing that it's supposed to do. So until then, you want the downstream consumers or dependencies to hold off and only read the data produced by the green job. So in order to actually build this notion of what is my current production primary, whose data can be used, we introduced another part of this blue-green deployment ecosystem called the configuration store, which is essentially just used to store the notion of a production primary. The configuration itself is fairly lightweight. It essentially is the service name, and it maps to the current production primary, which could be blue or green, and contains some other metadata like the timestamp. And so let's walk through what actually happens after these two jobs are brought up. How does this configuration store fit in? So we left off with the two jobs running green and blue. Green was the old one, blue was the updated one. And then the user comes back into the picture. The user wants to verify that the update was successful, that is, the blue job is running fine. They may look at metrics, they may check if they're getting paged or if alerts are being triggered. And if everything looks fine, they go ahead and update the production primary to blue in the configuration store. We use DynamoDB for this purpose. And once this update has been made, all dependent applications and consumers start reading or processing the data from the blue jobs sink. And then the user may determine that the green job is no longer needed. I just want to tear it down. I don't want to keep this green job running. And so they tear down the green job, and we end up in this state where just the blue job is running. And so basically, we also had to build as a platform team ability for users to be able to perform this update as well as the tear down stage. So this kind of completes the picture of the entire ecosystem around zero downtime upgrades. There are a couple of other considerations that have to be taken into account. Firstly, the whole deployment strategy assumes that there can be two Flink jobs running for an application at any given point in time. and which might mean that there's duplicate data being processed by two applications, and that the job should be okay with doing that. And secondly, it also means that uh, bandwidth availability for sources and sinks have to be factored in. In our case, we would either provision our Kinesis sources with extra shards to make sure that they can account for the extra job during the deployment period. And finally, it was critical for our users to be able to distinguish all of their observability data, like metrics, logs, alerts, etc., by the color or the version at any given point in time, because that's what would tell them which, when you have two applications running, which one is actually misbehaving during the deployment. And now we'll step into a demo that will show how this entire workflow fits together. So I started off running a simple Flink demo app. And now I'm going to make a update to the app. The update is fairly straightforward. I'm only basically changing the job name from demo to demo update. And I apply this update using our command line tooling. As you can see here, SP update. And the application itself is described in this JSONet file. And you can think of SP update as something like kubectl behind the scenes. So it just applies the application update to the JSONet update to the application. And once the update starts running, you can see that it's deploying the application and save pointing the job. It's creating a new cluster for the blue version. We started off with the green version. And finally, it ends when both the jobs are running. This is called the dual running state. I will also show you what it looks like for both the jobs to be running. You can see here that it responds with the status definitions for both the jobs, which is both, and you can see the deployed version is green and the updating version is blue. And it has all job details for both these jobs. And the current primary is green because that was the job that's currently running. And now we can also see that the new job came up. And with metrics, you'll be able to tell that there are two jobs that are actually running. And now I might look at more metrics. This is just an example. I'm just looking at the number of running jobs. I might look at more application-specific metrics to actually verify that the upgrade is successful and the blue application is running fine. And once that's complete, I decide to update my production primary to blue. We also use this SP command line tooling to do this update of the primary version. So it's just a set primary command with the color. It updates the notion of this production primary in our configuration store, which is DynamoDB. And once that's done, I can query the status again. The green application is still running, but you can see that the current production primary has been updated to blue. And once the production primary is updated to blue, I might decide as a user that I no longer have a need for the green application and decide to tear it down. And this teardown does a little bit more than just canceling the job and deleting the cluster. It does something extra like making sure that the green application that was running was not being served as the current production primary. It handles some checks to safeguard users from making malicious commands. And now if I query for the status again, I will see that there's only one application running, which is the blue application, which is the deployed version. There's nothing it's being updated to, and the current production primary is blue. So this completes the demo. And as for what's next, as you saw in the demo and in the slides, that the user sort of has to still do the validation and verification of the upgrade. I would see a future where some of this verification can be automated, and we provide custom validation hooks so that the entire deploy flow gets automated completely. And most of the work that is done here, uh, especially in the state machine, has been contributed back to our Flink Kubernetes operator open source project. And we're always working on more automated recovery and upgrade strategies. So if you're curious to check out what issues we're working on, or if you just want to find out more, please visit our GitHub page. We also have a Slack channel where we are pretty active, and contributions are always welcome. And with this, my talk is done. Thank you for listening, and I'll be live for Q&A.